So I'm going to start with the first one, which is about mouse implantation. I'm trying to go to the next slide. I am pausing, seems so. Okay, now it's playing. Okay, obviously, on this video is about cells in motion within the embryo, and the embryo is stratified in different tissues. And there is a better illustration of that on the next slide. So this cartoon describes the timeline of mouse implantation embryo. So right at the beginning, at the blastula stage, let's say, the mouse is made of three main lineages, like the epiblast, which is the brown tissue in the middle, also called the embryonic tissue, the visceral or primitive endoderm, that's the yellow tissue underneath the epiblast, and you have the endoderm, the pink tissue which surrounds everything. And then as it moves in time, there's further specification. For example, the endoderm is specified into the polar endoderm and the polar tropic. The ectoderm is specified into. All right. Yeah. All right.
Let you explain. Just speak over there if you want.
All right. Well, we'll just speak.
Yeah.
All right. Great.
So you might yeah.
Okay. So we're talking about the epiblast, that's the brown tissue in the middle. The visceral primitive endoderm, that's the yellow tissue, and then the top ectoderm, which is further specified into the neural ectoderm, the blue tissue, and the polar ectoderm, the pink tissue. Now, you can see that these different tissues, they undergo a lot of remodeling. The epiblast is has a kind of oval shape in the beginning, and then it's more like cup shape, and the ectoderm, the polar ectoderm starts with squamous cells, very horizontal, and then they're elongated. And so there's a lot of morphogenesis events that happen during this mouse implantation. And we're interested in a very specific event, actually, for our modeling. It's the transition from the very oval shape, kind of spherical, those not spherical here, that they're here, to the cup shape. So of the boundary of the epiblast. And the question is unique tissue. Perhaps you can see this space here, this is the epiblast here, and this space will be filled as soon as very soon move it. So the epiblast goes down and down. So two things, the shape of the epiblast from spherical top and then movement downwards. That's what we're interested in. So exactly. Well, that will be one of the points in my of my talk. So, I mean, this paper came out of analyzing this video, and this is not me. This is some people I work with. So the whole paper came out of analyzing these videos, and they came up with this hypothesis. So, but that's a very good point. It's not easy to see what's happening in such a video, and yes, one of my own things. So what drives then the epiblast movement and its shaping? So there have been hypotheses for the literature. So the first mention or the first discovery of the cup shape of the epiblast came with this study. They found out that the epiblast, yes, indeed, was kind of spherical in the beginning, and then it was it broke its symmetry and transformed into a cup. And later on, a study where the epiblast is the red one, yes. So later on, a study came about where they assembled stem cells and stem cells, and they kind of reproduced mouse implantation, at least some. And, so it's not the real mouse, so it's stem cells, like yes, lab produced, and found out okay, the symmetry breaking still takes place. So this tells us already that okay, probably the protector has something to do, at least. And then this later on, some experiments with just with the visceral endodem. So they found this epiblast cells which stem cells of visceral endodem, and nothing happens, no symmetry breaking. So again, it strengthens the hypothesis. But now this paper also from which the calculation comes from detailed the morphogenesis event in the trophectoderm. So the trophectoderm cells started very squamous, and then they elongated, grew their shape, and then they underwent apical constrictions. Apical constriction which caused the tissue to invaginate and push the tissue down, and also push the boundary down. So this paper describes it very, very neatly. And now, from these conclusions, we were then drawn to think that, okay, yes, maybe the trophectoderm has something to do with this remodeling of the epiblast. And because also now we have the steps, what is actually going on in the trophectoderm, maybe we can submit that to modeling. And if we want to model events like this, we need a model that can account for cellular shapes, because there's a lot of cellular movement and deformations happening here. So we devised a model in which each cell was represented by particles in motion. And between the particles, we have nonlinear springs, basically. So the edges are represented by nonlinear springs, and the elastic potential that we use, it's more potential between those. And also we put a central particle to represent the nucleus and whatever is going on within the cell. And with that, we then distinguish like a few forces. So membrane forces between two particles, that's what we call internal forces. So nucleus forces between particles and the nucleus in red. So here they are, and external forces. If you have two cells, more than the particles of the two different cells can exert mutual influences on each other.
Sorry,
Yeah.
It's very complex and deep. Can you explain exactly
Okay.
what is called?
Sure. So we have a single cell here.
The factors are not single cells.
No, the plastic are part of single cell because we want cells to be able to deform. Yeah. So, so all of this, for example, is a cell. And yes, on the cell membrane, this is what we presented here, but it's more. We have particles which interact with each other.
So it's a mechanical model of each cell.
Exactly. And then if we have multiple cells in interaction, also they can interact with each other.
So it's a 3D object.
Yes, a 3D object. Yes.
So these are all beads, connected by the frame.
Yeah, exactly.
I see.
And yeah.
Yellow yellow particles belong to two different cells.
The yellow connections, yes, means that these cells are interacting through these particles.
You have a four, the red one.
Yes, yes, exactly. This is how we define our nonlinear springs using a most potential. And okay, and we can see we can present deforming cells, and this is just another representation of the model. So,
so the equation of motion, this is the three equation of motion of the actual single cell.
Of the particles, of each particle.
Yeah, each particle which represents then
of course.
And the red set is the red element is the red color or the force.
Yeah.
Is
the force is how I actually define. So I have internal forces, nucleus forces, external forces. This is how I define the internal forces.
And what about the other one?
Okay. Yeah, this is the force that in phase itself on the membrane particle surface, but
Oh, I see, there is a force to the nucleus, and why the force to the nucleus?
so because the cell within the cell there's this network of what do you call it? The cytoskeleton, so which influences the cell surface and the membrane, which deform the cell as well. So for all this activity, yes, we put one particle in the middle.
So it's sort of an attraction force,
It's still a spring, like
green, but therefore they cannot become too large.
it cannot become too large. Yes. Yeah.
So is it necessary? Because I can imagine they also have, once you put them in 3D, then if you have a surface, there is some surface tension there, so you can become extremely large. So what's the goal of that? I mean, how important is that FI?
How important is that if I
So did you ever try to kill it?
Yes. One thing that happened when we tried to kill it, for example, and it's not here, but it's almost impossible to like transform itself from a convex shape to a concave shape without that. So it gives us a space of cells which is much more abundant than.
And can you say why that's the case?
I haven't thought about it.
Okay, it's okay. Just,
Sure.
okay. Thanks.
Yeah. Anyways, so I just want to point out that this potential is it's a spring, so it's attraction and retraction. So there's an equilibrium distance before which we have attraction and after which we have repulsion. So that's how the model works. And then now we can put a bunch of cells together, organized as trophectoderm and epiblasts.
Sorry, just one more. Can you go back?
Sure.
So that's on the spring and internal. So this is the interaction between all the little beads.
Yeah.
And so you have put in nonlinear because if you were to put linearly, I mean, put a linear spring force. What happened?
It's been shown in literature that nonlinear springs are better, represents biology better in this case.
What sense? If I see a cell moving, if I try to prevent to some, this is highly nonlinear as you couple all of them together.
Sure.
So what's the role of this nonlinear force?
Interesting. That I'll have to go back in literature and see.
Okay, so you can okay,
Sure. Yeah, but definitely, it has been shown that nonlinear springs are better, represent biology better than linear springs.
Okay.
So we then put a bunch of cells together in the configuration of trophectoderm cells, which start a little bit squamous, and then they grow up, and then they undergo apical transition, and also we have these blood cells there, and then yes, we can reproduce what was observed. Yeah,
this is very important. That's why we talk.
Exactly. Sure.
So how many cells have you put on the left figure, top left figure? How many cells are there?
Okay, we have 25 cells here. First of all, I want to note that this is a 2D cut of the 3D thing. So we have 25 cells here, and I think 50 cells now.
And they are very different, those two types of cells. Or no?
We're gonna get there.
Okay.
For the moment, okay, maybe if you look here, so these cells, for example, their height is very low at the beginning, and then it increases in height during the development, and then it forms a bottle shape. So there's a development scenario that's going here that is akin to what happens in biology. So, but here, these cells are all bottle shaped, and that's why they can form this mosaic, like they're concentric in a sense. But physically, at the moment, no, there's no difference. And well, but yes, with this, we were already able to reproduce what's going on, and also show that without the mechanical action of the trophectoderm, then the epiblast does not deform. Okay. And also, with the same experiment, we see that also the epiblast is being pushed down with these actions. So coming back to your question now, we did some sensitivity analysis of the model, so in what conditions does this experiment work? Does this implementation work? So what we did, we probed the elasticity of our virtual cells based on one parameter for our model. So we found that abnormality is J, that okay, the elasticity of the cells increased with our parameter. And then we run an experiment with multiple different parameters because we already showed the correlation between that. And we saw that, okay, this is the parameter for the protector themselves. I mean, this is the, no.
What is M? What's M?
It's a fitness.
Sorry?
We use a fitness metric to,
Fitness metric.
yes, here.
And what is that?
Okay, so to find out what parameters will yield a good experiment, we define metrics on these four experiments. So 3 metrics. We have the angle here. Let's say we have a point here and a point here and another point here. So this angle, for example, because it goes from spherical to flat, we expect the angle to be 100. Also, we expect this length to become basically diameter. So all of this is reflected in this matrix here. Oh, sorry, I will remove a lot of slides because time wasn't.
No,
So
okay.
yeah, sure.
Problem.
So then we compare, we switch the parameter space and we evaluate it according to our fitness metric. And we find out that, so I should add that here's the parameter for protector themselves, but the parameter for epiblast cells is like 2.5. I should put that somewhere. So we find out that the elasticity of protector cells should be slightly superior to the elasticity of epiblast cells. Yeah, in order for the experiment to work. And this was already confirmed in literature before, that the stiffness of protector cells should be bigger than the stiffness of epiblast cells. So yeah, that was your question about how the cells are different. So with the model, we can show that actually they should be. So, okay, so I'm going to go to the second study now. The second study, the pectoral fin of the zebrafish. So we're looking at this area here, and with the cells moving. At the beginning, the pectoral fin is just a very flat layer of cells, and then it turns into a 3D organ. I'm not sure if you can see that very well there, but probably here. So it's very flat at the beginning, but then so these cells are this color, but then yes, it grows another dimension, and we can see that the proximal distal dimensions that we increase, the other ones kind of stay relatively constant. Right.
So now the different colors there are important there. I mean, you have color coded in different ways. Those cells are there.
Oh, they're just important for this, but for the remaining of the part of the slides, we are going to consider them all just cells. We're not going to make any distinction between.
Okay, and then let me ask, but they don't seem that, the density doesn't seem that high.
Yeah.
And that's just a centroid because they are so cells.
It's just a centroid, like. Okay, so this we are working with collaborators who image these and then track the cells and everything. So we get this data of cells in motion. And what we want to find out is what drives the transformation of the pectoral fin from this 2D layer to a 3D layer. Okay. So in the literature, there are two main hypotheses driving this kind of limb growth. The first is the so-called growth-based morphogenesis, which just means that the pectoral fin develop a third dimension along the proximal distal axis. It means that there are more proliferation at the distal axis than at the proximal axis. So I want to show it again. Proximal end and distal end. The hypothesis says that as time goes, there should be more cellular division at this end, and then the cells will stack on top of each other and then form. That's what the hypothesis says. The second, that's what we're going to test. Okay, I can run it again. Yeah, it's not clear whether we see that, but that's what we're going to test.
There is some proliferation.
There is some proliferation for sure. Yeah.
The previous example, there was no proliferation.
No, there was no proliferation. Yeah. Yeah, and
also no active move.
No migration from one side to another.
Set. Just do whatever the mechanical equation of motion takes.
Yeah, yes.
Not move like,
no, they don't move far away from the initial position. They just change their shape, I would say. Yeah, adjust. Sure. Yeah. Yeah.
But
actually moving.
But I'm sure that the model of the beat, some random noise there, but it's stuff. No? No, not, maybe that's basically the same logic.
But here they seem to be actually moving.
Exactly. Sure. Yes. So with this remark, so the first model was very theoretical in a sense that we just had knowledge from the papers, and we use this knowledge to build a theoretical model to reproduce that, and also test our models against predictions that were already in the future. So the second model, we have a little bit more of data. You can see we have tracked cells, and probably we can use that. So the second hypothesis just says that, okay, it's actually the active movement of cells in preferential directions that drive the fin growth. So we wanted to test both hypotheses and probably model them. So the first one, we counted divisions. We divided the whole thing into bands, and within each band, we counted divisions. So here, for example, these are divisions along the AP axis, divisions along the PD axis. This is actually what we're really interested in divisions along the distal ventral axis, the PD axis.
So this is integrated over time.
This is cumulative. Yeah, exactly. Integrated over time. Sure. Yeah. So the broad-based hypothesis said that if that was true, we were going to count more divisions at the distal end than at the proximal end. But this is not what we observe. And even when we divide it in bands, in relative bands, like because the fin doesn't have the same height at all points in development. So even if we divide that in relative bands, we just don't see that. So we thought that this was enough to discard this hypothesis. Then the second hypothesis. So what we did is kind of then shape of the pectoral fin at the end of the development, and it's okay. So the yellow points represent cell centers, and the surrounding matrix like around the cell center is what we would say is the cell shape. For example, we don't have cell shape in the data, but just merely. So
So sorry, that one is the final thing.
Yes, or let's say the fin form at the point in the road, at the point in the road.
At some point.
Yeah.
in time,
Yeah, at some point.
Right.
Right. So we have the cell centers which are given by the point we have, but also we have here, let's say, imaginary cell shape. Like if we have, right, we can get that with Voronoi and that on explanation. So we look at the longest axis of cell, the longest elongation axis of cells of every cell, and
wait, that
Yeah.
you look at elongation axis, you said that you don't have the cell edges,
okay,
so then what kind of measure is that?
okay. So cells can have if I think it would be reasonable to think that if neighbors of cells are farther away, then probably the cells are longer. The center of neighbors are further away than the cells, maybe.
No, it's true, but
Yeah.
the point is that where do you put those white points? It's arbitrary, no?
Yeah, but this is just a cartoon. Like,
I know.
Yeah.
Even if it's just a cartoon, your data, you said that there are no vertices in the data. That's
yes,
what you heard.
Yeah.
That's what I heard from you.
sure.
Therefore, your white points are arbitrarily chosen. Therefore, how can you rely on the direction measurement?
All right. Okay. So what we have is just the yellow point.
Yellow point.
Yes. What we do is that we act upon the hypothesis that cellular shape can be inferred from the distribution of cells around a cell. The cellular shape of the shape of a cell can be inferred by the distribution of its neighbors.
Ah,
Okay, yes. So we have the Voronoi neighbors, and then we create a Voronoi. How do you call it? Pixelation. Yeah, pixelation, and then from that we infer the shape of the cell and then the elongation axis. At least, yeah. So then we compare the elongation axis of the cell with the proximal distal axis. We get the angle from this tree. And this is here, this is the proximal distal axis, and this is the elongation axis of cell, the Y. And so first of all, we computed that, and then we observed. Let's play a game. So at the beginning, everything is flat, kind of. But then it tends to align with the proximal distal axis. And this is confirmed with this measurement of the angle. It goes from perpendicular to it decreases. Some value. Okay. Oh yeah. So this is the mean angle between a cell elongation axis and the proximal distal, let's say the black one, and standard deviation.
Okay.
Sorry, good. All right. So, well, this already tells us something that yes, probably cells tend to have preferential directional behaviors in order for this pectoral fin to grow in the proximal distal axis. But we want to test that using modeling. So a model is usually determined by many things, among which the data on which model. So in the previous model, we wanted to explicitly represent cell shape. Here, perhaps we don't need it, so we go for a center-based model. Again, we have a cell center and we have its neighbors. And let's say with the Voronoi, we can so again, we represent the interaction between neighboring cells with an attraction repulsion force, again, a Morse potential. And then, because we just saw in the data that cells actually want to align their longest axis with the PD, we add a polarization force. We add a polarization force. So the equation of motion is the attractive and repulsive potential between cells plus the polarization. And this is how we define the polarization force.
So it just now in the past you had beads at those corners from the previous model.
Yeah.
Yeah, it's different.
Here, the cells are just represented by points. That's it.
Each cell is one part.
Each cell is one particle.
What about those?
It's just a Voronoi.
Yeah, but then if you go on, if you have an arrow there, something's happening there. What I mean,
Sorry?
so that's a Voronoi.
Yeah.
Distillation. So there is another center particle somewhere else.
Yeah,
So what those, okay, the blue arrow, what does the blue arrow represent?
the force, the attractive repulsive force.
And so, and why do you have this, in a sense, do you need that Voronoi distillation, just that point part?
Well, probably I don't need in this representation. But
Okay, now I understand. So you don't need, so that was confusing to me, if I have a Voronoi or not. So if that's
No,
just
I
one
didn't-
particle,
I know we have a bunch of particles, but I do need this in my code. Maybe not in representation, because it's from the Voronoi that I compute the elongation at longest axis of cell.
so in other words, in the model, when you run the model,
Yeah.
you every time, so there is a force which is through the center.
Yeah.
But then to decide what the direction, you tessellate with a Voronoi,
Yeah.
and then you find the direction, and now it's
Sure.
updated like this.
Yeah.
Measure the shape.
I get it.
Great. So we have two forces: attraction, repulsion, and then polarization force. Or yes, and again, we're able to replicate the decrease of the angle between the cell longest axis and the PD axis, and also have a model where the vector often goes only in the PD direction and not in the other direction. So, and okay. So here again, we need centrally analysis, which is not very interesting. But
Wait.
yeah, sure.
Hold on. Because with these models, what you get is the right shape, it's aligned with the PB axis. But
Yeah.
they seem to also move away from the equatorial plane.
Oh,
You can see anything.
yeah, sure. I mean,
What the-
okay. So sorry.
That-
Yeah.
So besides the alignment.
Yeah.
You see that they change the overall shape, so they seem to be moving away from the original plane.
Sure. Do I have to move it here? No, we do see that because there's proliferation, like more cell and then attraction repulsion.
So they have-
Yes. Yeah, they move away and the polarization force and everything. So, yes, I didn't put a video, sorry, of the simulation.
You model the proliferation.
Yes, we did add the polarization model. Yeah. All right. So in the second study, we used a little bit more data. Actually, we went through the data, and the data informed our modeling in a very real way. So in this third study, we even went further in the data analysis, and we are now wanting to see how we can use this data analysis, this kind of data analytic method that we developed to model the system. And that's part of what I'm going to be doing here. So acidian are kind of invertebrates that live in the sea. They're good they're good as models of biological development because they have few cells. The development is very quick and even transparent. So, and there is a lot of literature covering early acidian development. earliest movements made of cancellation, of nervation, and there are interesting division patterns and interesting cellular movement patterns that happen during the early development of gastrulation of ascidian. So gastrulation, for example, okay. So in gastrulation, for example, you have the ascidian embryo. So this is the animal pole, and this is the vegetal pole. In this developmental period, you have divisions happening mostly on the animal pole, and very, very few on the vegetal pole, and even later. That's one, and second, you have this invagination that happens in the vegetal pole. The invagination is driven by epiderm cells, endoderm cells, sorry, by endoderm cells, and it was shown that this invagination happened in two phases in a sequential way. So there's the first phase and the second phase, and then once castration is over, there is the beginning of novellation. I might show, no, I don't have a video showing that right now, but basically the invagination happens like a zipper, like closing a zip, like maybe I can show it later. Okay, from the two projects that we showed earlier, the first one, as Luca very well said, we cannot see anything from the movies. And mostly that's how biologists, they investigate morphogenesis. Look at the movie for months and try to analyze cells. And I have the privilege to work with PhD students, with other PhD students who are doing that work. And it's really, really hard, and you will get sometimes like I couldn't see anything, I was crying because I couldn't see anything. So sure. So the eye test is very limited in that thing. But even if we manage to see something interesting, the scale in time and in space, so very difficult to distinguish if it's just one thing happening or if there are many things happening at once. Even if we observe a significant movement, we don't know what actually individual cells do. And as we've seen also, like the matrix to even describe these movements, they are very dependent on the type of movement. For example, proliferation, we have to count cells. Folding, maybe we look at the curvature and everything. So the metrics are very dependent on the type of movement that's observed. And because of that, they are not fit for scale. So we then need an automatic method to detect and localize interesting phenomena in morphogenesis. Okay. So in order to do this, we want to quantify deformations across the embryo in the most generic way possible. And we do that by computing the strain rate tensor at embryo. So now we have data from developing ascidian embryo, image data, and we are working with collaborators in Montpellier who have designed a very nice pipeline that helps transform this data into meshes, geometrical meshes. So we have individual cells, and you can see that there are few challenges with this data. First of all, there are volumetric meshes of single cells. Second, the meshes that we receive, they are not uniform, so we don't have also we use the whole thing again. So what we want to do, we want to, based on this data, to create an evolving embryo surface, to create a mesh that represents the evolving embryo surface. And if we have that, and if every vertex of this mesh in time, then maybe we can compute velocities and stuff like that, and then we can analyze the movement in a very interesting way. So in order to do that, we use a level set method. This is, for example, the surface of the embryo with many cells. And if we have, let's say, or for which we know the connection between the vertices, we can match the shape of the embryo by using this level set thing. So the embryo is a 2D surface. In the 3D space, it's not non-self-spotting. So our sphere is homomorphic to that. So we can find a map that transforms the sphere into the surface of the embryo. And we do that by minimizing the distance between the two surfaces. So I have to rush a little bit because also my laptop is dying, and time is also going. So, for example, at given time point, we have the sphere, and then we can involve the vertices, and we see an example of that. Yeah. Now, for the next time points, we can do the same thing, or we can also exploit the surface of the embryo computed at the previous time point. And with that, we have the original embryo cells, and then we have the mesh. If you can see that where individual vertices attract. So we can have a Lagrangian, we can follow Lagrangian trajectories of these vertices. And here, this is a quantification of the error on that. And we can compute velocities between two different time points. So here's what the strain rate looks like then over the surface of the embryo. So first of all, it's a tensor, so we can compute the eigenvectors, and this is the eigenvectors field of the tensor. But what we will be interested in right now is this scalar field, which is derived from the eigenvalues. This will tell us how the strain rate evolves in space and time. What we can notice is yes, that's HPF, ours post-phase acceleration. Great.
We have a
There isn't anything remotely like this in mathematical form.
No, yeah, but I'm saying that formation, best tensor, the rate which best thing power around the So I'll keep waiting on that. So initially,
Sure. I just need to plug in. So, yeah, so reds represent areas where we have higher motion or higher morphological activity, and yellow and green and yellow and black where we have lower. Thresholding can be better, I guess. But for example, I was talking about invagination, for example. When we have invagination, it's red because we have a lot of morphological activity here. And also here, it's red because we have a lot of proliferation. We'll come back to that. And this is what this is the beginning of neurulation. I was talking about a zipper earlier. So you see this, if you have a zipper and you close it like this. Yes.
One side of the opening.
Yeah. Yeah, exactly. So that's how neurulation starts in the embryo, in the ascidian embryo. So we have this data then we want to analyze it. We want to go deeper. Like this, it's already good to see where there is a lot of morphological activity, where there's few, not much morphological activity, but we cannot distinguish between a lot of things here. So one thing that we can do, because this is, we have a scalar field on a surface that is homomorphic to a sphere, we can use the spherical harmonic decomposition to analyze this. basically, spherical harmonics decomposition, spherical harmonics are this basis of harmonic functions, which are very useful to decompose any function or signal defined on the sphere. And yes, the goal of the decomposition, as usual, is to find these coefficient elements, which we can find using that. Just to illustrate.
You have to explain it to your subscribe when they don't see it.
All right, so this is another representation of the scalar field that I just showed, but like century and time evolved like this, and this is the decomposition or the reconstruction of the decomposition using spherical harmonics, and we can stop at the degree because you look like. I mean, it's like Fourier transform. Actually, many people call it the 2D Fourier transform. So it goes to infinity, but we can stop at the maximum. So this is my signal. Oh my God, sorry. All right. And we see that as the decomposition goes further, then we are able to reconstruct the signal. Like this looks very, very similar to this. I don't know if it's we didn't see that. Yes, but not so much that. So that's just to. So and we can map the canonical functions on the back of the embryo. So, for example, at this time point, here is spherical harmonic y 0 0 y 0. Yeah, 0 0 1 minus 1 1 0 and 1 1 and so on and so forth. So we have this all these functions, and they act also as eigenvectors.
Sorry, can you, if you go, because I can see the time now.
Yeah, sure.
In terms of, I see a slope there of that line in terms of the number of cells. No?
Yeah.
What's the rate? So can you tell me with the rate at which is morphogenesis propagating?
Which the proliferation.
Yeah. I don't know. I want to know the rate. Information time. I want to know that rate.
It's 100 per hour.
That's interesting. I wouldn't.
I'm expecting that the information that they are gathering, so that all of these processes happen. We have not talked about chemicals before.
Yeah.
It seems to just,
Physical. Yes, mechanical. Sure.
mechanical.
Yes,
So,
polymechanical.
so isn't that surprising? People talk about, chemical gradients and stuff. Is what? Is that you're sort of modeling the new thing because there is no chemicals involved, or what?
No, well, there's the chemical view of morphogenesis, but there's also the physical, the mechanical view of morphogenesis, which is also a lot booming right now. Like, yes.
And so the point that because nobody mentioned the chemicals, it's very hard to figure out. Is that true?
I would think that most people measure the chemicals. And
Whenever I talk to cell biologists, chemicals, I mean, they say there are chemicals, but nobody is able to make. I mean, the chemokines, nobody, they say they are there, but nobody is able. Every time you look, okay, I don't know about morphogenesis, but in general, cell biology experiment, it's very hard to know which chemicals that follow, because I mean, how do you make?
Yeah, probably it's difficult to establish causality.
Yeah,
Yes.
Measure it.
Okay.
So it's very difficult. It's one of the few cases now. So it's very hard. So what I'm saying is that, so now you're saying it's more, the fashion that people are increasing more on the mechanical, or because there is a missing information about the chemical, so people have started looking into the mechanical part.
Definitely, the chemical don't tell the whole story, and the mechanical also don't tell the whole story. It's the coupling of both that tell them.
Right.
Yes. All right. So this curve, why do we want to show it? We want to show that as we decompose, yeah, first of all, this one. So the harmonic functions act as eigenvectors. So it's, let's say it's a PCA, and we want to see the variance ratio of each PCA. Here, the first harmonic accounts for 64% of development. And the other one on the middle here accounts for, the next one accounts for 4%. And you can see them represented. And the reason I have this plot here, the dynamics of cellular population, if you show, interesting that you asked about the rate. It's difficult to measure because it's almost a step function.
No, right? You can just imagine that you draw a line.
Yeah.
With that. So if I ask you, can you do it for us? You're going to draw a line.
Yeah.
And then you tell me what's that rate.
Well, sure, we can do that. I mean,
5 cells per hour.
sure, yeah.
No, but
100
it's 7 cells from 64. Oh, yeah. It's a factor of 100 vertical.
Yes.
Just, you know, if you can
Sure.
tell us precisely.
Yeah, I can tell you definitely, and maybe it's interesting for your use cases. Yeah, but I wanted to draw your attention to the bonds, like the steps. Yeah, exactly. I want to show that it's aligned to these peaks. Of,
Okay, yeah.
Yeah,
We
because
can
no
call-
classification is okay.
yeah, exactly, because division is a very it's a very high mechanical event in the cell, and once they divide the cell count increases, and our spherical harmonics are able to detect that. That's what I want to show. Yes, and also yeah. So
These are in the measurements.
these are in the measurement. These are in the measurements. So what I'm trying to say is that we started with some projects where we actually have to count the number of cells to know that there's been a division or anything. Do you even know that in the first model there was no cell division? There was cell division. So if we have a new data, for example, we don't know a priori whether there is one or not. But this very generic and agnostic analysis can already tell us that something like this happens. And we can even go further. If we these are time series, and if we do a wavelet analysis of the composition of this time series, then we can even know further more about development. So, for example, this very high frequency event, the division, and this the evaluation I talked in the beginning about, and here is the sequence in the narration. And yes, we can identify so much more about development by no prior knowledge, just looking at data in a very agnostic way. So yes, towards data-driven models of morphogenesis, and we can do that the same with a mutant embryo. And yes, this then we can move on. And how can you use this data to model morphogenesis? How can we learn, for example, the constitutive laws of this active matter? And also, what can we learn about development from looking at cells purely from their physical space? Yeah, I guess that's what I want to talk about today. I hope it was interesting to you as first. Thank you.
So,
We're going
go ahead.
to do a model, an elastic model like the previous one.
Exactly, with this data. But because we have a lot of data here, we have basically the evolution through time. Maybe we can go a little bit further. Like, probably we can try to learn maybe the constitutive laws of this material. For example, you know what I mean. So,
So,
Yes.
I mean, first, it's a curiosity. Do you have an image of an amphibian? Once it's grown up,
Sure. Once it goes,
But the mouse and the therapy,
we know. All right. Can I just?
So I was just curious what it looks like.
search it in Google.
And then, I mean, I can do it later, right? So at the work. So no, but the other thing I wanted to ask you then, so how long does it take for the, I mean, if you go back to some of the figures that you showed
Yeah,
us,
sure.
like
Okay.
for the main
Want to asking about the rate?
example,
No.
there, for
Yeah.
example, okay. Okay, because this is, you know, I didn't follow you the detail about what gas relation, neurulation, and so at some point, this process ends, no?
Yes. At some point, this process end, and
And where are you? You're there.
yes, this is also one thing that this method does. It tells clearly when one ends and when the other starts.
So it's like,
The calculation ends.
The relation ends, yeah, and the relation starts.
so the duration is an hour, I see that.
It's 2 hours, 2 hours. 5 hours. The duration of that duration.
Okay, so it's 2 hours.
Yes.
And so I was just trying to compare that 2 hours. If I go and go back to the previous slide, that the total process is 2 hours. Yeah, I can tell me time, HPF, hours,
Post fertilization.
and then here I see that it's go from 4 to 8.
Yes.
Tell me what do I mean? There is a total process which is on the gas rate, which is 2 hours.
Yeah.
And here I see 8, I mean 4 to 8, 8 hours, 4 hours.
Yes.
2 hours.
Okay. Calculation and relation for the
Oh, that's the whole thing.
yes. It's a whole.
I see. Okay,
And you see that the behavior of the spectral decomposition is different. The first half and the second half.
oh, yeah.
Different process.
Exactly. Just the different process. Yeah.
Okay,
And we can see it more clearly here. Yes.
so is this material published or not?
All of these studies are published.
Okay, please send me and Guillermo the references for,
Sure.
especially this, I mean, actually, all of them. You can send it.
Yeah, sure. I can do that. Yeah.
Great,
Thank you.
thank you so much.